All right, like I said, we got to get going here so that we can finish here right at 4:30. And so you have an opportunity to get to Aki's tutorial on model selection, which will, I think, build on this a little bit, because one of the really important things with model selection is choosing which among various hierarchical models you might prefer. So goals for the second half here. So we left off, we did a hierarchical model with the RStanRMR package. And Richard McElraith, who is going to be giving a talk here tomorrow and has written a book, really argues forcefully that these hierarchical models ought to be the default way of approaching Bayesian modeling. It wouldn't make sense in most situations to use a non-hierarchical model when modeling data, because there's always going to be some heterogeneity that you would want to be taking into account, or at least you couldn't rule that out until you actually estimate those models. And so you can click on this link and get one of the chapters from his book on hierarchical modeling, and it's using Stan behind the scenes via his rethinking package. So we want to learn more how to estimate these hierarchical models. We want to use BRMS, which we'll do next. And then towards the middle and towards the end, we want to start to learn about some transformations that you can do to improve the efficiency, left off an E there, of the way Stan can sample from these hierarchical models and build ourselves up to where we can start to specify some of these hierarchical structures ourselves in the Stan language when writing a Stan program. So BRMS, it's another package, uses Stan behind the scenes. It has pretty much one estimation function, which is called BRM, that's used to estimate all of its models. So here we have a model using the data set on roaches. It actually comes in the RStanRM package, but it's used in some of Andrew Gelman's books. But basically, it's a simple model here. It comes from an experiment on the prevalence of roaches. And so here we're saying that the roaches that we observe at the end of the experiment are a function of the number of roaches that we observed at the beginning of the experiment, and the effect of some treatment variable like a roach poisoning, something that was applied to these buildings. And because roaches are integers, we use a Poisson likelihood to specify this. But what's cool about this model is that we're not necessarily saying that log number is a linear function of the previous number of roaches. It could be a nonlinear function. And in fact, with a lot of animals and stuff like that, we might have reason to think that it's like an exponential function. So the more roaches that you have at the beginning, the more roach babies they're going to have. And by the end of the study, you're going to have way more roaches than you had at the beginning, or at least that's possible. As far as I know. We have a lot of roaches in New York City, so hopefully you don't. Anyway, a model like this can also be represented in hierarchical model form, where your linear predictor eta is equal to x times some common coefficients plus z times some deviation in those common coefficients. And this is really talked about thoroughly, although not necessarily from that Bayesian perspective, by Simon Wood, who's the author of the MGCV package in R and has been for 30 years or something like that, even going back to the days at S. But he has a new version of his textbook out recently that you might want to look at, and a lot of the syntax that's used in that book can be used equivalently with RStanRM or BRMS. So this S function says we are specifying a spline, and so what basically the way in which BRMS does this is says, okay, we want it to be a spline function of the previous number of roaches. We will make that spline function. We'll represent it with knots and a bunch of basis functions, and then linearly combine those together to form this additive but nonlinear function of the previous number of roaches. And we want to estimate how much curvature and stuff like that there is to this function, which can all be captured by hierarchical modeling this, the standard deviation from one coefficient to the next. And we'll see how this works. So we specify that syntax, pass it to BRM. This requires that you have a C++ compiler installed, because it's going to build the Stan program for you and compile it locally, unlike RStanArm, which comes with compiled models from CRAN. Anyway, it'll take 30 seconds or so to compile, and then like 2 seconds to obtain the output, which can be summarized like this if you just do print or a summary of something produced by BRM. We see a bunch of stuff at the top about what model was estimated. We have at the bottom a section for what is called population level effects. So we have an overall intercept. Its posterior mean is about 3. We have a treatment effect estimated to be negative, and it's pretty precise, so that's good. Whatever treatment they use to get rid of the roaches seem to have some effect. And then we have a coefficient for the linear part of the spline. And so it's estimated to be 3.5 or so in its posterior mean. But we've said that function doesn't necessarily have to be completely linear throughout the whole space. And in the middle part there with the smooth terms, we can see the standard deviation, which basically captures how much curvature there is to the function relating past roaches to the log of current roaches. We see, again, a pretty high and reasonably precisely estimated standard deviation pertaining to the curvature. Now, that's a little bit hard to interpret, but BRMS has like a plotting function for these nonlinear models. And if you call that, you get something like this describing your posterior distribution. So you can see why it said, okay, there's a positive relationship between the number of past roaches and the predictions for the number of future roaches. But actually, there's a considerable amount of nonlinearity in this relationship going on here. It seems for like buildings that have a small level number of roaches, it's actually a pretty flat function. Once you get up to about 200 roaches previously, then it's a pretty steeply increasing function. But it actually peaks when the number of previous roaches is a little bit over 300, and maybe like there's not enough food or something for that many roaches. And then it's a decreasing relationship for very high number. And so that is sort of captured best by this plot, but it's sort of hinted at by saying, okay, there's an overall positive relationship, slope about 3.5, but there's considerable standard deviation around that, which gives us basically a nonlinear predictor that looks something like this before we add on or subtract, really, the treatment effect for this. And so the ability to make plots like this, and the gray is 95% credible interval, also showing your uncertainty in what the relationship between past roaches and future roaches is. For some of these, in the data, sometimes you don't have a whole lot of data points to be estimating the curvature of this function, and it's going to be reflected in wider confidence intervals around 400 than 200 or 300, which is, I guess, a more conventional number for roaches in the buildings where this study was done. And so this is basically no harder than estimating a generalized linear model in Stan. It's not super hard to do this from a frequentist perspective either, but you don't really get the same interpretation of the uncertainty and the ability to like propagate that uncertainty through your predictions and your evaluation of the, how effective this treatment is and everything like that. So the ability to basically take the syntax of MGCV, and you can do this in RStanArm with stan_gam4, you can do it with BRMS, but to take the syntax of MGCV for specifying splines, or the syntax of LME4 to specify group structures, and use the innovation of the Stan algorithms to get draws from that posterior distribution and then to be able to interpret the output, is a really good and useful thing. And you'll find, if you do this a fair amount of times, that the problems that you run into with trying to do this with LME4 or MGCV, it not converging or something like that, local optimum, those sorts of things. The frequency of problems like that compared to the problems if you estimate this with Stan, you'll have a whole lot fewer problems doing this using Stan, and you get all the interpretability, the ability to describe your uncertainty that you get from any Bayesian approach, and with basically no increase in difficulty to the user, except you have to install Stan. That's about the most difficult part of the process. Yes. So questions about this part? It's really just another way of specifying a hierarchical model where the important part of the prior is like how much curvature there is in this function and where the curvature occurs. And like I said, there's additional arguments where you could specify your prior, saying, before you see the data, is this likely to be a pretty linear function, or is it conceivably a very nonlinear function? That's really what's captured by the prior standard deviation on this sort of curvature parameter in a model like this. Where'd my, yes? Questions about that? Nope. I get to throw this later. Okay. Okay. So how does BRMS do what it does? One of the things that's good about BRMS, better than RStanArm, is that the Stan programs that it generates are a little bit more readable, because they're only intended to estimate or to correspond to the model that you estimate, as opposed to all the models that you could estimate. If you want to estimate a different model, BRMS will generate you a different Stan program. But another thing that's good about BRMS is that in addition to the BRM function, it exposes the make_Stan data function and the make_Stan code function. So you can look at the Stan code that it generates and learn from that. And when doing so, it's good to keep the list of data that's being passed to Stan handy, so you can go back and refer to it, the different things, in order to understand the Stan program better. So we can see in this case, BRMS is creating a list of 8 things to pass to the data block of a Stan program. N, which is the total number of observations, 262. Y, which is an integer array of one-dimensional that goes up to 262 for the count of the number of roaches at the end of the experiment. NB, I forget, but it's 1. Knots is 8, which is the default number of knots when you specify a spline in BRMS for this nonlinear function that's going to be sort of specified piecewise in such a way that it links up and the first derivatives are the same at the knots. It has this Z matrix, which it calls ZS for Z smooth. Anyway, this is a 262 by 8 matrix. Each of the columns of this are going to be one of the basis functions being used in the spline. So it gets multiplied by its appropriate coefficient when making the linear predictor. K is the number of coefficients that are common. So it's the intercept, the coefficient on the treatment effect, and the linear part of the spline. So there's going to be a 262 by 3 or 262 by K matrix X that's going to hold all of that. And a flag, in this case, is 0, saying, do you just want to draw from the prior, or do you want to draw from the posterior distribution? And since prior only is 0, we're going to be drawing from the posterior distribution. So these are the data things that are being passed to the Stan program, which we're going to look at next. And so if you call make underscore Stan code, give it the same information, it will put out on your screen what the Stan code that it's used to estimate a model like this. So this comes with a number of code comments, but we're going to walk through it just so that everybody can kind of understand. And certainly if you have questions, raise your hand or shout out if I don't see you. So the first 8 things here are just going to correspond to the Stan representation of these 8 things which constituted our list of data that we passed to Stan. So it's the same stuff. Number of observations, integer array that has the counts of the outcome, number of common coefficients that go into our regression, an n by k matrix that holds those predictors, and then we have stuff pertaining to the smooth function or the deviation from linearity in the function relating past roaches to future roaches. So NB equals 1 is the number of, NB1 I think is the number of smooth terms, which is 1. An integer specifying the number of knots, which by default is 8, but you could specify more or fewer. A Z matrix that sort of has all these basis functions in its columns, and prior only the flag saying, do you want to draw from the prior distribution, in which case ignore the likelihood, or if that's 0, condition on the data and draw from the posterior distribution. In the transform data block, really all is going on here is that we're centering the columns of the X matrix. So centering is something that is a really good thing to do in Bayesian models. It reduces the dependence between the coefficients and the intercept in the posterior distribution. And so it's basically a kind of almost free way to get better efficiency from Stan by reducing the posterior distribution. The only thing to keep in mind, and this can either be a pro or a con depending on how you look at it, is the interpretation of the intercept changes. I think we were talking about this before with a class size of 0. That doesn't really make sense. If you center the predictors, now the intercept should be interpreted as your expectation for the linear predictor when the predictors are at their sample means. Now, oftentimes, that's actually a good thing. It's easier to think about the prior distribution that you want to use on the intercept if it's sort of the expected outcome for an average observation, as opposed to, when all the predictors are 0, which might not even make sense when we're talking about class size or age or something like that. Anyway, in the transform data block, all that's going on here is creating XC, which is a centered version of X. So subtracting the column means from each of these predictors and taking away the first column, which is all 1s, because we're going to estimate the intercept separately. So questions about the data block or the transform data block? Yes.
So in the BRM notation, you don't have to specify the number of bases like manually, but here we obviously have to.
So you don't have to specify the number of
bases.
Oh yeah, knots in the spline function. Yes. So by default it's 8. You could specify S roach1 k equals 4, and then there would only be 4 basis functions. Or you could do k equals 20, and there's 20 basis functions. So you can change that, but by default in BRMS it's 8.
Okay.
For a single spline, like univariate spline. I can run.
Just 2 syntax questions. You used BRMS to specify this model, right? How did you, where's the code that specified that you wanted to center your variables?
Okay, and then you had another question?
The second question is the line of data equals r stan arm : roaches. How is that? I'm just wondering. I haven't seen that syntax before.
Okay. Yeah. So confusingly, the roaches data set is in the rstan arm package. So it's just saying, look in rstan arm for this data set. It's really not a hugely important concept, but the : syntax in R basically says, look for something in the package on the left. So rstan arm is the package, roaches is the symbol that has that data set. The more important question, the first one, how do you know that, how do you tell BRMS that you want to center the predictors? And the answer is you don't get a choice. BRMS does that for you, or it does it internally. And if you didn't look at the Stan code, you might not even realize that it was doing that, because it's sort of strictly better to use centered predictors because it makes Stan more efficient. So there's really no option to center. It's going to happen for you whether you like it or not, but you like it. And so that means you don't have to center your predictors yourself, like in the original data set. It's all going to happen internally. Oh, I'm running out of battery. All right. Better? Hello? Okay. Yes. Author of BRMS here.
I just wanted to tell you how you can turn it off. So if for some reason you want to set a prior on the literally intercept, right? So that happens rarely. Then you can write 0 plus intercept, and then it will work. So there's a special case implemented in BRMS to be able to turn this off. But you rarely, if ever, want to do that.
So you just mentioned how centering predictors can make Stan run more efficiently. Does the same hold for centering one's response?
No. Actually, it doesn't make it run more or less efficiently, but centering the response is slightly wrong, because the response is a random variable. And so if you condition on its mean when you subtract it out, technically you need like another part to model the mean, but that's not being reflected anywhere. So it doesn't help, but it gets the uncertainty a little bit better if you just leave the response as is. Now, one thing that you can do, and this can make a difference, rstan arm, BRMS, whether you're doing things in Stan, is scaling variables by constants. And so a lot of times if we're talking about income, euros or dollars is not a reasonable unit if you're talking about someone's income. You should probably scale it into thousands of dollars or thousands of euros to talk about like a change of 1,000 euros might have a noticeable effect on the thing that you're studying, whereas a change in income of €1 is probably unlikely to have a noticeable effect on anything that you could possibly hope to measure. And so scaling the variables by constants to put them in more appropriate units for the priors that you want to place on those coefficients and things like that is both a good idea and it can help Stan be more efficient. But in terms of subtracting the mean from the outcome, basically there's no need and it makes it slightly wrong. Other questions? Yes.
So I have one more question about the centering. So suppose I have a model specification where I use a logarithmic transformation on the predictor. So centering gives me negative values and I lose these values. Is there a possibility to deal with this?
Yes. The centering takes place after the transformations. So if for some reason we wanted to use the log of Roach 1, then we would say S log Roach 1. It would first take the transformation. That actually happens in R. Then it would expand the thing out into basis functions. Then it would center the linear part of the spline as a function of the logarithm. Now that's more complicated than needed. The spline function can handle any nonlinear function, so usually you're just putting stuff in the raw units. But you don't have to worry about it centering first, creating negative numbers, and then taking a logarithm, which would result in an error. The transformation happens before the centering. Others? Okay. Okay, so we're comfortable with the data and the transform data blocks of the STAN program generated by BRMS. Okay, so now the rest of the blocks. So this is going to consist of the parameters block, the transform parameters block, the model block, and the generated quantities block, although the generated quantities block didn't fit on the slide here. But if you type that on your laptops, you can see it. So we have the number of coefficients. This corresponds to 1 per column of the centered X matrix. We have the intercept that corresponds to the centered predictors, which is called temporary intercept, and actually in the generated quantities block, which you can't see here because it got cut off, there's a transformation that basically undoes the centering. So the posterior distribution of the intercept reported here, 2.96, that is the posterior mean of the intercept corresponding to the original uncentered predictors, which is probably the one you want for inference, but for efficiency reasons, we tend to want to do centering. So we've got the temporary intercept, and then we have the parameters that correspond to the deviation from linearity in the smooth function. So we have pieces that correspond to each of the knots. Like I said, by default there's 8 of those, but you could have specified more or fewer. And then we have a standard deviation parameter that's restricted to be positive that governs how much those z's, how far away from 0 they can be. And so basically in this setup, you can think of it like this. If that standard deviation is small, all of those z's are going to be pretty close to 0. And then that's the deviation from linearity. So there wouldn't be that much deviation from linearity. And the linear part of the previous roaches would sort of dominate the predictions for the future roaches. But if the standard deviation turns out to be kind of large, which it did in this case, then these basis functions are going to capture bigger deviations from linearity in that relationship. And that's really what happens in the transformed parameters block. This is another instance of a non-centered parameterization. It's used a lot in RStanArm and BRMS, and when you write your own Stan code, it's often a good thing to do. Scaling up these z's by the estimated standard deviation in order to get the coefficients that go on the columns of the Z matrix. And so all that happens at the start of the model block. We create something called mu, which is a little bit misleading because it's not actually a conditional mean, but you can think of it as eta. That is the centered predictors times the common coefficients B plus the Z matrix, which was created outside in R, multiplied by its scaled coefficients to capture the deviation from linearity, add on the temporary intercept that corresponds to the centered predictors, and we have our linear predictor that goes into this Poisson likelihood that you can see the statement on that at the end, again with a target plus equal deal. All the lines in the middle are the priors, and these are, since I did not specify anything about the priors in this example, these are the defaults that are used for a model like this. Since estimating nonlinear functions is not super complicated, especially for something like Stan, but it's more complicated than just doing like plain OLS or something. You might want to give more consideration to these priors, but in any event, these are only the default ones, and you can look in the documentation of BRMS as to how to specify or look at, there's like get prior and set prior to do these things. But anyway, a T prior on the temporary intercept with 3 degrees of freedom, that's going to have pretty wide tails. Normal prior, that's pretty standard on these basis function deviations. A half student T prior on that standard deviation governing how much nonlinearity there is. So that is the reason why there's a subtraction here, is because it's a half T prior for this thing that is constrained to be positive, and so you need to truncate away the mass to the left of 0, so that can't happen. And then, like I said before, the likelihood statement is just saying the logarithm of the expected number of roaches is equal to mu or eta here. Questions about how these lines play into it? And I should mention before I forget, in the generated quantities block, which you can't see here, there's a couple of things that might go on in a BRMS model, but one thing that's usually going on is undoing the transformation from the centering that results in the temporary intercept to get as a generated quantity the posterior distribution of the intercept that you would have obtained if you didn't center the columns of X in the transform data block, which is going to correspond more closely to if you did this and you wanted to compare it with MGCV, you would probably get pretty similar answers, at least for the posterior mean or the posterior median. So it's always good to have sort of the same parameterizations that you can check against in one of the original packages. So questions about how this works?
The question about the knots, are they going to be inferred or they are knots?
The cut points?
So they're vector of knots, or knots. Are they going to be inferred or they are located on the grid and they are fixed?
So different splines sort of handle the nonlinearity in the different way. Here, the number of knots are fixed, and there's some stuff that goes on in the MGCV package as to like where to break them up the function in the when you specify it in R. But the main thing that makes the biggest difference is estimating the coefficients on each of these basis functions. And so basically, you could move the knots around a little bit and if you just make corresponding changes to the coefficients on the basis functions, you would get pretty much the same nonlinear function coming out. Now, if you do it extreme enough, like you specify 200 knots or something like that, then yeah, it can start to make a difference. But for reasonable choices, and I think the default is pretty reasonable, it doesn't matter a whole lot. But there's many options not being shown today in the MGCV package that are picked up by both RStanArm and BRMS for different sorts of splines. And so if you're specifying like a spatial model, and the things are like longitude and latitude, that's a different sort of spline corresponding to a Markov random field than some of the other ones. Or you can do a Gaussian process for the nonlinear function, in which all of these are going to have different options that you can specify for the details of how you want the nonlinear function to work. But basically, for this, as long as you specify enough knots to capture the relevant nonlinearity, then it doesn't matter too much exactly how many knots that you specify or where it is in the distribution that they cut. You can make the corresponding changes to the coefficients to get reasonable predictions out. Question over here? Nope. Okay. Okay, so before we get into kind of writing our own Stan stuff with hierarchical models, we need to talk a little bit about reparameterizations. And we've already seen this come up a couple times because it's pretty common among people who are experienced writing Stan programs. But we want to talk about it a little bit more formally, this idea of a non-centered parameterization of a distribution like the normal that is in the scale location family. So distributions in the scale location family, like the normal, you can write a general normal random variable as a mean plus a standard deviation times a random variable that is standard normal. So if you take something that is standard normal, multiply it by some positive constant, then the product is going to be distributed normal with mean 0 and the standard deviation equal to that positive scaling factor that you used. If you then shift it over by some constant mu, then that resulting thing, which has been not only scaled but also shifted, is going to have a general normal distribution with mean 0 or mean mu and standard deviation sigma. And so the fact that you can use both or either, really, representations of a normal distribution, either taking something that's standard normal, scaling it and shifting it, or just going with a variable that has a normal prior with mean and standard deviation, whatever you specify, gives you sort of two opportunities to write your Stan program in the most efficient way possible. Now, it's not always clear going into it which parameterization is going to result in the best efficiency, but we've found probably the more times than not, using the so-called non-centered parameterization, where you take something standard normal, scale it up, shift it over, tends to work better than the other parameterization, the centered parameterization. Now, you need to know how to use both because sometimes one is more efficient than the other, but probably to start with, you want to tend to use the non-centered parameterization. This is also known as the Matt trick, after Matt Hoffman, the person who wrote the original version of the NUTS algorithm. So to understand what this is, let's sort of simplify it back to the case we were talking about earlier, like the schools example, whatever, where the only thing that is varying across groups is the intercept. And so we might think that the school-specific intercept has, a normal distribution with some overall population level intercept alpha that's unsubscripted, and sigma or tau, whatever you want to call it, capturing the deviation of the intercept from one school to the next. So sigma or tau, the standard deviation of the intercept across groups, is an unknown parameter, but it's constrained to be positive, and when you specify something that's positive in the parameters block of a Stan program, behind the scenes, Stan is going to introduce yet another variable, here let's call it omega, and take e to the power of omega in order to ensure that sigma is positive. But really Stan is drawing from the posterior distribution of omega and everything else. You just don't see the omegas, but they're actually there. Anyway, the normal distribution, like I said before, can be characterized or can be generated from a standard normal distribution. So take a standard normal, scale it up by sigma, shift it over by alpha. The distribution of that random variable is going to be normal with mean alpha and standard deviation sigma, and that applies to other things besides just the normal distribution. It works to the t distribution and some other things. And so you can often help Stan sample efficiently, which is more important than it sounds, even though it already sounds important. Like, you want your Stan code to run as fast as possible, but you also want it to mix throughout the parameter space fast enough for the means that you calculate afterward to be reasonable estimates of the analytical posterior means that you can't calculate. And in order for those to be good estimates with a finite amount of draws, you really need the Markov chain to mix throughout the parameter space really fast. And Stan can do that for a wide class of models that are differentiable, but sometimes it needs a little bit of help. Or it can be like not great efficiency under one parameterization, but really good efficiency under another one. And you want to figure out which one that is and base your conclusions of your study on the more efficient one. And so you'll often see something like this in Stan programs with this transformation, where we have something, let's say, like U, which will, a vector of those will declare in the parameters block. And then when it comes to the model block, we'll put a standard normal prior on U. And then you'll see in the transform parameters block, or maybe in the model block, you'll see this scaling and shifting going on in order to create the alpha j's, which in this case is the thing that we really want to interpret, the school-specific or the group-specific intercepts. And so by putting a standard normal prior on U, that reflects we have these general normal prior beliefs about the alpha j's, that they're distributed before we see the data, normal with expectation alpha and deviation sigma, where sigma is represented by e raised to the power of something to ensure that it's positive. And the reason why this often is good is because with the Stan algorithm nuts, it's essentially only taking into account the first derivatives in the logarithm of the posterior distribution, but it's exploiting that information in the first derivatives in order to move around the parameter space as efficiently as it can. But it doesn't utilize the second derivatives. And that's okay as long as the second derivatives are reasonably constant, reasonably close to zero. Where its algorithm can get itself in trouble is when the second derivatives are large. So the posterior distribution, the shape of the density function, is changing rapidly from one part of the parameter space to another. And you can see this a little bit if you look on the next slide and you run this in R. It pops up a RGL thing, so I couldn't do it in the slides, but I'll try to do it now. So this is the surface corresponding to the first, I can't show both of these, maybe I can. No. Can I move this over? Oh. No. No, I blocked out my slides. All right. This surface here corresponds to the first function being plotted, which is sort of the non-center or the centered representation of the normal prior. And you can see it's not super apparent, but if you turn this thing around sideways, you can see that as omega goes from like ranges from -2 to 2, the surface of the distribution here is pretty flat throughout most of the range. But as omega gets to very extreme values, the second derivatives are very large, and the slope of this changes rapidly in log units. Like at the top, it's about 0, and then it all of a sudden gets changing very, very rapidly. And down here at the bottom, it's like -100 in log units. So basically, it changed by about 100 as omega went from -1 to 2. That sort of second derivatives, which Stan's algorithm is not taking into account, makes it hard. Stan has to take really, really small steps when the function is changing underneath it that rapidly. So this is a very sharp, steeply changing function. And then if we do it with the non-centered version, which basically is scaling and shifting a standard normal, we get something that looks about the same overall shape, but it's changing much less rapidly. So it's implying the same distributional beliefs about the alpha j's. They have a normal distribution either way. But in the non-centered reparameterization of the function, now this is only ranging from like -1 to -2.5 throughout the range of omega. So, omega can change from relatively big to relatively small, and the function corresponding to the log density only changes by like a couple points, as opposed to falling off a cliff changing by 100 in the space of a 1 unit change in the omega. So you can play around with the code for that to convince yourself that it is making a pretty big difference to the second derivatives, which is what's really relevant for the efficiency with Stan. So if we go back to the example we talked about before the break, this thing where we had an interaction term and the coefficient on age was a noisy linear function. I said at the time we were using, a non-centered parameterization where we take noise, which we give a standard normal prior to, scale it up by sigma, so that sigma times noise, before we see the data, we believe that has a normal distribution with mean 0 and standard deviation sigma. But by doing the non-centered parameterization here, we make the second derivatives not change as much and make the function better behaved, easier for Stan to deal with, and that would probably be advisable for something like this. We could use a centered parameterization where the data and the parameters block are going to be the same as they were before, except now I've put beta age in the parameters block rather than the model block. So beta age is now primitive. It has the same role. It figures into eta in the same way. But now we've specified a general normal prior on beta age with mean equal to λ1 plus λ2 times income and standard deviation sigma. So that is the centered version of a model like this, which is legal Stan syntax. Stan would run, but it would probably mix not very well. And you would get warnings about divergences, or maybe the chains don't converge. They have high R hats, could have low fraction of Bayesian missing information, all the things that tend to spit out warnings, which you should take very seriously, because it's basically Stan is telling you, I can't sample from the posterior distribution you defined with the standard of efficiency that I usually can achieve. But if you were to flip back to a non-centered parameterization, that would probably work reasonably well. Like I said, sometimes centered parameterization is best, sometimes non-centered parameterization. It's hard to tell in advance. I would usually tend to start with the non-centered one. If there's anything that we can say about which one is likely to be better in a particular situation, the centered parameterization tends to work better when the outcome is measured with very little error. So maybe physical measurements of something. And you have a really theoretically informed model of these things, and you can estimate almost anything really precisely. Sometimes in that situation, a centered parameterization will work better than a non-centered parameterization. But a lot of things in the social sciences or biology, ecology, stuff like that, where things are going to be measured with a lot of error. We don't necessarily have theoretical models to explain all these sorts of things. We don't have any real expectation that we're going to be able to estimate things super precisely. In that situation, the non-centered parameterization tends to be better. But it's hard to say any sort of absolute rule, so sometimes you have to try it both ways. That said, RStanArm and BRMS basically only do non-centered parameterizations for things like this, so sometimes you have to take the code and then change it if you want to do a centered parameterization. So before we go on to the multivariate case, is there questions about this idea of the non-centered reparameterization just in the univariate case? Yes. So let me get this.
Yeah, I was wondering, is it conceivable that Stan would also take these second derivatives into account? Or is that fundamentally impossible because of Hamiltonian Monte Carlo or something like that?
Look out.
Just in the wrong place.
So in a manner of speaking, it is fundamentally incompatible with Hamiltonian Monte Carlo, but the idea of taking a second or higher derivatives leads you to Riemannian Monte Carlo. And I would say it's reasonable to hope that Stan will have that in the near future. Actually, we already have the algorithm. It's not exposed. The main thing that we're waiting for is to be able to do forward mode auto differentiation. So to build out the math library, it's been reasonably complete with reverse mode auto differentiation for many years now. But the forward mode auto differentiation, which is really needed for stuff like Riemannian Monte Carlo, has been lagging behind. And I think that is sort of the main reason why the Riemannian algorithm hasn't been exposed yet. And yes, so we don't have a whole lot of experience with it yet because it hasn't been released into the wild. In principle, having Riemannian would make it less important whether you choose the non-centered parameterization or the centered parameterization, and that Stan would run efficiently either way. But because it's taking the second derivatives and actually the third derivatives, it has to multiply by a matrix of second derivatives and get the action of this matrix. Anyway, it's complicated stuff. Anyway, there's a lot more stuff to compute, and that is going to slow it down. And so if you could do Hamiltonian Monte Carlo nuts with a non-centered parameterization and have it work well, then that's probably going to be faster than Riemannian, which would also work well, but has to compute a lot more stuff on the way, and it's going to take more time. So you do still need to be cognizant of a lot of these things. Also, 2 years from now or whatever, it may come to the case where you're doing an example so difficult that even Riemannian Monte Carlo doesn't go particularly efficiently unless you use, so there always, like, as you get better advances in algorithms, people are more ambitious in the models that they estimate, and there'll probably come a day when you have to use a non-centering or a centering or something like that to get even Riemannian to go efficiently. Other questions? Okay. Okay, so that was the univariate version of the non-centered parameterization. There's also a multivariate version, at least based on the multivariate normal or other elliptical distributions. And so if you have some vector of coefficients, perhaps including the intercept, that is specific to the jth school, something like that, you might have a multivariate normal prior on that with mean vector mu, covariance matrix sigma. But that can a lot of times be difficult for Stan. So if some of the diagonal elements of that sigma are close to 0, then all of the betas, corresponding to that column have to be in a pretty narrow range around mu. So nuts is going to need a small step size to handle that. But if sigma, the kth diagonal element of sigma can be large, then the betas are going to fall in a wide range around mu, in which case Stan is going to need a big step size in order to get around this whole big area of the typical set in the posterior distribution. But you can't have a step size that's both big and small at the same time. And so if the diagonal elements of sigma are not estimated particularly precisely in the posterior distribution, so there's posterior mass where it's small and posterior mass where it's big, then Stan sometimes it's going to need a small step size, sometimes it's going to need a big step size for the same posterior distribution, and it can't do that. So it goes with the small one and it just takes a long amount of time, but if it's not small enough, you can get divergences and stuff like that. So the multivariate version of the non-centered reparameterization, or the multivariate Matt trick, which I don't think Matt actually talked about, but we just attributed him to anyway, is to use the stochastic representation of the multivariate normal, where you have a bunch of u's that you declare in the parameters block, they have a standard normal prior, and then in the transform parameters block, you take those mu's and you pre-multiply them by L, where L is the Cholesky factor of the covariance matrix. I think we talked about Cholesky factors briefly, but didn't really define them. So Cholesky factor is like the square root of a covariance matrix. But it's a little bit different because matrices are a little bit different from scalars. Anyway, L is lower triangular. All of its upper triangular elements are 0. It has positive elements along its diagonal, and it has free elements below its diagonal. And sigma is constructed such that sigma is equal to L times L transpose, perhaps multiplied by a scalar, in this case, sigma. Anyway, so you can take U, pre-multiply it by a Cholesky factor, scale it up by the standard deviation of the errors in the observation, shift it over by a mean vector mu, and the distribution before you see the data of beta j is now multivariate normal with mean vector mu and covariance matrix equivalent to the sigma that you started with. And so when you specify one of these hierarchical models, both in RStanArm and BRMS, they're going to be doing it matrix. Actually do the priors on some of these parameters by default a bit differently, but the idea of using a Cholesky factor and the stochastic representation of the multivariate normal distribution is something that you really, really often want to do. So there's some cases in the univariate case where a centered parameterization works out better. Most of the time when you're dealing with a vector, so multivariate situation, the non-centering thing tends to work better, because not only do you have variances that you have to worry about, you also have covariances. And if any of those gets a little bit sticky, then the centered parameterization can really suffer. And so you see, people who are experienced doing STAN often using the non-centered parameterization when doing multivariate stuff. So that leaves the question, well, what are the priors that you should be putting on like L and sigma and all sorts of stuff like that if you're going to use multivariate normal priors, either in centered or uncentered form? What would be the priors that you might want to use on stuff like that? So in the previous decades where people were mostly using Gibbs samplers, you saw a lot of like inverse Wishart priors on a covariance matrix, and nobody had any idea what those really implied, and you couldn't really specify a meaningful prior on something that you didn't even really understand. With STAN, you're free to do what makes sense, and what often makes sense is to decompose a covariance matrix into a correlation matrix and standard deviations. So we can factor a covariance matrix into standard deviations and correlations. Correlations, much easier to deal with than covariances because they're bounded between -1 and 1. They don't have units, so that's advantageous. Also, specifying a prior on the standard deviations separately is something that a lot of people find a little bit more intuitive than trying to do a prior on a covariance matrix, which mixes the correlations and the standard deviations together to form those covariances. So we can represent a covariance matrix as a diagonal matrix of standard deviations multiplied by a correlation matrix lambda, post-multiplied by a diagonal matrix of standard deviations on the other side, and we get a covariance matrix. So then we've sort of pushed back the question, well, what priors should we put on standard deviations? We've already had, slides and stuff about that. Exponential is a good choice. It's maximum entropy for a given mean. Half normal, half t. All of these can be reasonable choices for standard deviations. But that leaves the question, well, what should be the prior distribution on the correlation matrix lambda, which is a little bit of an interesting beast because down the diagonal, the elements are fixed to 1. They're not even random variables. But the off-diagonal elements, it's a symmetric matrix, but at least the lower triangle is going to contain random variables. And so in STAN, well, mostly in STAN, but I guess it exists outside of STAN a little bit, probably non-informative prior for a correlation matrix. Because a correlation matrix, the space of those is a convex set, it's possible to specify a prior that is uniform over that set, which is not possible to do if you try to specify a prior on a covariance matrix directly. And so this prior is called LKJ in the STAN manual. That's because me and Bob could not spell the authors of the paper that wrote this, whose names are actually Lewandowski, Kuro, Fishka, and Joe. But we couldn't spell that, so we just made it LKJ. It has this representation of the density, a constant, a determinant of the correlation matrix raised to the power eta minus 1. So if you set eta equal to 1, then you're just raising this to the power 0. That's going to be constant. In general, this acts like the shape parameter of a symmetric beta distribution. So if you specify equal to 1, the whole thing is going to be constant. If eta is greater than 1, then the density is non-constant, but the identity matrix is the mode. So identity matrix is the modal correlation matrix. And as eta gets large, you get more and more concentration of this density around the identity matrix. If eta is between 0 and 1, identity matrix is actually the least likely correlation matrix, and that's something that does not seem to make a whole lot of sense in a lot of situations where we want to model, where we think, okay, maybe there could be some correlations, but we don't think that error terms are like super correlated a lot of times. In that situation, you might want to say eta is like 2 or something like that to give a little bit of concentration around the identity matrix, but not too much. You can also specify a prior on the correlation matrix, on the Cholesky factor of the correlation matrix, such that the correlation matrix as a whole has this LKJ distribution as its prior. So if you do this in, we'll do another example with BRM. It would be pretty similar in our StanArm. Take this data set from the LME4 package, which was a study on how much people's reaction time is undermined if they don't get any sleep, or if they have to take a flight yesterday from New York to Finland. Anyway, we specify the number of days that you're not allowed to sleep and allow the coefficient on that in the intercept to vary from one person to the next. Some people can deal with that better. Anyway, that's the data set. The data, pretty standard stuff here. We have 2 z's, so one of these is going to correspond to the intercept, which deviates from one subject to the next, and the z12 is going to correspond to the subject-to-subject deviation in the coefficient on days. We only have one sort of LME4 stanza here, so there's only one grouping level, but we have a J which sort of indicates which observations pertain to which subjects. I believe there's 18 subjects overall, and they're observed 10 times each, although this is not exactly a proper time series being studied here. So assuming the observations within each person are conditionally independent given the parameters. So we've got a data block which corresponds to the R representation of the list of data. Transform data block, again, Paul is centering the columns of the X matrix, pulling out the intercept, introducing a temporary intercept here, and then reversing that in the generated quantities. So in the parameters block, we again have the coefficients on the common predictors, which in this case there's only one, the number of days without sleep. The temporary intercept, the sigma, which is the standard deviation of the errors in the reaction time measurements. Then we have SD1 and Z1, which pertain to these deviations from the overall effects from one person to the next. Don't want to go into too much details about that because we have already kind of seen some examples. I want to focus on the Cholesky factor correlation line of the block. We have Cholesky factor core of size M1. M1 is going to be 2 in this case, and we call that L or L1 because there's only one grouping level phenomenon going on in this model. And so those are both the common parameters and the primitives of the individual level deviations. And then in the transform parameters block, we do something that basically is equivalent to this line here, taking our primitives, pre-multiplying them by a Cholesky factor of a correlation matrix, scaling that up by the estimated standard deviations that we're estimating. In this case, there's no shift because the prior on these individual level deviations has a center of 0, so we're only doing the scaling part. And then, we stick those into the respective columns of this R1 and R11 and R12, which then go into the linear predictor for this in the model block, the first line there. So first line just does the common parts, multiplying the centered x by its coefficient, shifting it over by the temporary intercept. And then there's a loop that comes through here and adds on the individual deviation on the intercept and the coefficient on the days without sleep parameter. We have to use the J1 ID variable to see, which observation corresponds to which person, and so we use double indexing here. That works pretty much the same way as it does in R. So now the linear predictor, which in this case actually is a conditional mean, is now fully specified, and it gets a little bit cut off here, but there's more priors and ultimately a likelihood statement, y is normal given mu and sigma. So really, the thing to study a little bit more on is just this process of filling in what ultimately ends up as mu, this mean vector of conditional means, from tacking on the stuff from the Z matrix and stuff like that. And since we're estimating both intercept and coefficient deviations from one subject to the next, those can be correlated, and that's captured implicitly by a correlation matrix, but explicitly by a Cholesky factor of a correlation matrix, which is really just kind of like the square root of a correlation matrix. And so that's kind of a lot to go through, particularly if you're not that familiar with matrix algebra, but it's something to maybe take an hour, read through the Stan manual on it, read through the slides more carefully on it. So if you need to do it yourself, you can. So Aki actually wanted me to end a few minutes early, so I'll do that. But for those of you who want to stay around, you can ask some more questions. But sort of as an exercise to walk away with, Juho Pyronen and Aki recently wrote a paper where they derived what Andrew Gelman calls the Finnish horseshoe prior for regression coefficients, which is similar to the original horseshoe prior, and it has this idea that your prior on a regression coefficient should be like centered on 0, but it should have really heavy tails because you might have one of these predictors that really does have a big regression coefficient. And so how can we specify a prior that sort of shrinks small coefficients to something very near 0, but doesn't put very much shrinkage on big regression coefficients? And it might, at this point, not be too surprising to you to say, well, you should use hierarchical structures in order to sort of reflect that belief that a lot of people have about regression coefficients, particularly when dealing with a lot of predictors, and like in maybe a genomics situation where you only think maybe a handful of these have a noticeable effect, and there's like a million other genes or something like that that have no effect on your susceptibility to some hereditary disease or something like that. So we have coefficients that have a mean of 0 and a standard deviation that is a product of tau, which is called the tau, the global scale factor, and these lambda tilde j's, which are the local scale factor. And so this allows tau to be big. So overall, the global scaling factor might be large, but any particular lambda j could be close to 0, in which case there's going to be a lot of shrinkage if you take something like tau, which is big, and something like lambda j that's small. If lambda j is small enough, that's eventually going to dominate. And so then, okay, what are the priors that we want to put on tau and lambda j? More levels of hierarchy, more level of saying, a distribution for one thing depends on another unknown parameter, and we're going to estimate the posterior distribution of all that stuff. So it's sort of an exercise. You might think about, okay, if I was going to do this myself, which of these things would go in which block of a Stan program? And once you've figured that out, or try to figure that out, you might write a Stan program that has k predictors, no necessarily like LME4 style stuff, although you could build that in 2, and try to do it for like a linear regression model that has k predictors, each of those having this finished horseshoe prior for its coefficients. So, do as well as you can with that, and then you can click on the link to the original article in the appendix. They actually have the Stan code that they used, which is equivalent to this, but it's also going to have a whole lot of hierarchical stuff, whole lot of non-centering going on in order to make it efficient and avoid divergent transitions and stuff like that. So you can try that, but in conclusion, for those of you who want to get a quick break before Aki's model selection tutorial starts, just to kind of wrap up what we've been doing this afternoon, you really should be using hierarchical modeling unless there's a strong reason not to, and you wouldn't know that there was a strong reason not to unless you'd estimated a hierarchical model and found that there was no heterogeneity going on in the first place. So basically, use hierarchical modeling. It comes up in so many places once you learn to sort of think in terms of conditional distributions and stuff like that. It's pretty straightforward conceptually from a Bayesian perspective, more conceptually straightforward than trying to do these with the frequentist stuff, and you get all the advantages in terms of propagating your uncertainty, being able to use stuff like LU and posterior predictive checks, which we didn't have time to talk about specifically in the context of hierarchical models, but everything that you may have heard or will have heard over the next couple of days about that applies to hierarchical models just as well. But when you start to do the pushing this, more bleeding edge stuff, NUTS is certainly the best choice, the best algorithm out there for doing hierarchical models, and it was originally conceived in order to do these more difficult hierarchical models that bugs has difficulty sampling efficiently for. And so NUTS is already doing a pretty good job for a lot of hierarchical models, but there's a decent percentage of these sorts of things where one parameterization can make Stan work really well, and another parameterization Stan doesn't work well, or it works like okay but not great. And so being able to do things with like different choices of the parameterization, non-centering, centering, using different distributions, thinking about the tail heaviness and stuff like that, can make a big difference, but they can also help you think about your data generating processes in ways in which it makes it easier for you to specify priors. And we saw that with the sort of decomposition of the covariance matrix things. We're able to get away from inverse Wisharts and stuff like that nobody has any idea what they even mean, so you can't specify a prior on that. Break it down into little pieces until you're comfortable specifying a prior on those pieces, and then compose the thing up in the transform parameters block. And so in the case of a covariance matrix, if we just decompose it into a correlation matrix and standard deviations, we've got good priors for correlation matrix and good priors for standard deviations. And we can use those on the things that we declare in the parameters block. Stan will work pretty good, and you can, in transform parameters or generated quantities, you can make the covariance matrix if you want to do posterior inference about that, or posterior prediction, stuff like that. Anyway, I'm going to stop talking, but I'll stay here if some of you have questions about what we talked about in the second half. For those of you who want to get to Aki's model selection tutorial, that starts in like 8 minutes, so you might have time to get some water or something like that before it starts. But he will build on doing model selection for some of these hierarchical models, sorts of stuff. So anyway, thanks for coming. See you around the rest of the week.